I think then we might get started. Today's webinar will be provided by Dr. Pandora Hope, and it will be on understanding past and future extreme events and their causes. Pandora Hope is a principal research scientist at the Bureau of Meteorology and a lead chief investigator of the Earth Systems and Climate Change Hub Project 2.2, which is entitled Enhancing Australia's Capacity to Manage Climate Variability and Climate Extremes in a Changing Climate. Pandora has over 2 decades of experience researching Australia's variable climate with a focus on Southern Australia's rainfall trends. She's been working with a great team of researchers to extend the field of attribution science for the last 5 years and is currently leading an international team to describe the range of attribution methods for the IPCC, or the Intergovernmental Panel on Climate Change, 6th Assessment Report, which is due out in 2021. With that, I'll pass straight over to Pandora to begin her presentation. Thanks, Pandora.
And I will work out how to unmute. Hello, everybody. Can you hear me?
Yes.
Excellent. So, as Sonia said, I'll be describing past extreme events, but I really mean by past and future very near to now. So don't think far-flung future and don't think far-flung past. So I also make the point, I do work at the Bureau of Meteorology, so thinking about how we can turn these, also with the NESP, Earth System and Climate Change Hub, into a service, I guess. What does attribution science mean around these climate extremes? So if we cast our mind back, hang on a moment, why is this not? To 2012-13 summer, the angry summer. A lot of you might have remembered graphics such as this, which describe many of the extreme temperatures. I can see a 49-degree there now, which broke a record set in 1958, a 47.8 over in Western Australia, and a few other really steamy records through that summer. And we think about, well, what caused that and why do we care? So if we have a look at the time series, we can see it really was the most warm summer on record, and as we look at Australia as an average. So what could have caused that? Was it internal variability? So what is internal variability? Well, that's really circulation set up by the distribution between the equator, where the sun hits full intensity, transferring that heat through to the poles. And the circulations that get set up, the instabilities in the atmosphere and the ocean, that's internal variability. And it can be things like ocean currents, as we can see there on the right, and also over Australia, the weather systems that hit the south, tropical cyclones that hit the north, El Nino and La Nina from the Pacific, and the Indian Ocean interactions, as well as higher latitude processes. So all of those go on without any other external forcings. So if we have a look at the global temperature series over time, in blue we have years following a La Nina event. And you can see generally they're cooler, if you have a look at around 2000 here, than a year following an El Nino event. So there's definitely an impact from these sorts of internal processes. But if you look at this graph again from 1950 through to now, there's something else going on. Pretty much we're poking the earth, I think. We're changing what's happening with external forcing. So what are some of the things we're doing? Increasing atmospheric greenhouse gases, changing aerosols, particularly particulates released by industry, Antarctic ozone hole changes, and those can be described as due to human activity or anthropogenic forcing. Other external forcing, as we term them, are the variability of the sun on about an 11-year cycle and volcanic eruptions, which you saw in that global graph, brings us generally cool conditions, often for 2 years after the volcano, if it's in the tropics. So what does all this mean? We can then attribute what's going on in any particular extreme event with science of attribution. And these are exercises intended to connect an observed change to one or several drivers and to quantify their respective contribution. So they allow us to understand the drivers of the changes we are experiencing in the recent past. So it can link observed changes in the climate to natural or human-induced forcing or to internal variability, depending on the method used. But the really important thing is that quantifying the link between human-induced forcing and extreme climate events can help us prepare for a changing world. So if we find that a particular extreme event did have a strong contribution from human-induced warming, we can say this extreme event gives us a window into the future. This is the kind of thing we would expect to see more of in the future. If we have a look at the kinds of extremes that have had attribution studies done around them, back in 2012 or before, there were a number of studies, particularly around heat extremes, and these might be month-long extremes or heat waves. Also, there were efforts to look at extreme rain and flooding events. There was one in the UK. And through time, people have tried to look at many other events, such as drought. And drought's a really complex feature, and so we really need to consider what aspects of it is actually being attributed and to what. So the framing of any of these sorts of questions is really important. You can see now in 2018, there are a whole host of kinds of extremes that have had attribution studies done on them, still many on heat and temperature and rain and flooding, but also this one in purple, what's that? Ocean marine heat waves is also an emerging science. In terms of what Australian scientists are doing, often they do studies on the Australian region, and that's very true across Australia here. 7 studies on Australia-wide heat extremes, 1 on frost, which is actually in southwest WA, and circulation changes. You can see there in the Bight, which is actually about Tasmanian rainfall declines. And in the red are where the studies have found a human influence. So believe it or not, there was a human influence found on those frost events in southwest WA in September 2016. And quite a few of these are being led by NESP scientists. Michael Gross from CSIRO led the one in WA. Myself and the team at the Bureau have led quite a few across other parts of Australia. So these little thermometers here are the temperature extremes. The raindrop are the extremes precipitation events, and that little fire one is also one we tried using a hybrid method that I'll get to later. So how do we do this? The simplest way to describe it is that we usually, and this is not always the case, use 2 climate model simulations, one with anthropogenic forcing and one without. So if we have a look at this time series, which is from 1910 to 2005 in the grey, we've got simulations from global climate models of Australia's annual temperature. And the range is the range across the different models. There's about 42 different models included in this plot. The time series you can see overlaid on that is the observed time series with a 10-year running mean through it of the temperatures. And you can see that 2012-2013 summer. So the 2013 average is the warmest year on record, or was. And in the blue, you can see simulations without human emissions. So if we were to compare the two, we have straight away an attribution study. If we can find a class of events in the natural simulations, we can compare how often they occur there to how often they occur in the simulations with human emissions. So this is one type of attribution method, and it can really be used to assess how likely we were to pass a certain threshold, to pass a certain record. Another method is using something called weather at home. So this is an atmosphere-only simulation run on sea surface temperatures that are prescribed over a regional domain. And there are thousands of simulations run because they're run on home computers. You can sign up to this if you want to and run this on your home computer. Specifically looking at our region, you can see in the yellow there, the Australia-New Zealand region. And we run simulations with current sea surface temperature conditions. So it might be of, say, the year 2016. And then we also run the same simulation, but we take off an estimate of the global warming since pre-industrial times. An example's down in the bottom there. And pretty much it's warm everywhere except for regions of the Southern Ocean. Again, this is something we can do after the event, once we have those estimates of the observed sea surface temperatures. A third method, using the same idea of running two climate models, one with and one without human forcing, is a seasonal forecasting framework that we've been developing at the Bureau of Meteorology. And for this, we use two forecast ensembles of the event, one under current conditions and one where we assume that no atmospheric carbon dioxide increases have occurred since about 1960. And to do that, we remove an estimate of the ocean change since that time due to carbon dioxide, an estimate of the land change and the atmospheric change from the initial conditions. And I'll go into that a little bit more later. So those are three of the methods, but there are others, but also including ones that are based just on observations. So back to 2012-13. So there were quite a few attribution studies done on this particular event. One aspect of it was that there was internal variability leading into the event. So a positive Indian Ocean dipole means a reduced chance of rain across Southeast Australia in the preceding spring. So there were dry land conditions preceding this event. The first thing we really do when we're using any attribution method, if we're using a climate model, we'll test the model against observations. So that's what we've done here, or rather Lewis and Caroli from 2013 have done. So in the observed, you see the anomalies from each year through the century compared to a change from early last century, 1911 to 1940. So in many instances, the change is around zero. Actually, it's no warmer or cooler than it was as an average over that early period. But in some cases, it's warmer by around 1 degree. And in some cases, it's cooler, also by about 1 degree. And overlaid on that, we have the models and their anomaly in this same configuration. And we can see, again, it has a very similar structure where most of the anomalies are around that climatology value, with some warmer and some cooler. And so we can look at the probability of exceeding the previous record, which was in 1998, and what 2013 looks like on that distribution graph. If we then look at the current climate, so this is from 2006 to 2020 as an estimate of the current climate, and we can see that those anomalies compared to a climatology of early last century have really shifted up to a warmer, I don't know if you can see that arrow. So here's 2 degrees more, which was well outside what we saw in the previous graph, and even up to 3 degrees more. And so the probability of exceeding that 1998 record was at least 5 times greater. Looking at observations alone, this is from similar to the graph in State of the Climate 2016. It wasn't actually presented in 2018, but it really shows that in that more recent period, in the dark red there, 2003 to 2017, a extremely warm, like 2 standard deviations, like 95% higher than the usual temperatures. This is monthly temperature average right across Australia for the daytime temperatures. They might happen now about 13% of the time, whereas earlier in the middle of last century, even just 1951 to 1980, it only happened less than 2% of the time. So that really gives you a sense of how, if we've got a background trend, our extremes will be changing in their probability of occurrence. If we now look back a little less, we can have a look at the summer of 2018-19, and I'm not sure we actually need to do an attribution study. The anomaly is so much greater than the warmest year on record was previously. It's really quite astonishing. Sophie Lewis has gone ahead and done a quick study and found that it's almost impossible that this could have occurred without the background trend in temperatures. Here are some of the fun facts about that particular summer. Port Augusta saw near 50 degrees, 49.5, and just a little bit further inland at Verona Downs, they had a pretty steamy night with 36.6. Hobart seemed lovely with 6 days above 30. I don't think they're used to that. So if we go back to using a seasonal forecasting framework for the attribution of climate extremes, we've used this to look at quite a few different events. And the really great thing about this is that we can look at the forecast outlook and see, is there any extreme event being forecast? And then we could run an attribution study. So we can make attribution statements before the event has actually occurred. So seasonal prediction is an initial value problem. The future's weather or season's climate is determined by the conditions that are used to initialise the forecast model. So we try to get the best estimate of the observed state. And going back to that slide I showed earlier, for the current conditions, we really do try and get those observed conditions as our initialisation, as our initial state. For the one with no CO2, we lower the carbon dioxide back to 1960 levels, so about 315 parts per million compared to what it is today, which is 110 parts per million, and we take off these estimates of warming in that time. And you can see right around Australia, the sea surface temperatures in this left-hand graph are quite warm, but we actually modify the full ocean temperatures right through its depth and salinity. And the same with the soil moisture is actually drying out in the southeast of Australia. And we capture this change in the structure of the atmosphere, which actually has an effect on the circulation patterns as well, which I'll talk about very much later in the talk, depending on how time goes. So one event that we looked at was October 2015, which had an anomaly of 3.44 degrees, with some temperatures 6 degrees above normal. Now this is a relative anomaly. It's in October, it's not at the height of summer, but these anomalies are important for things like crops or other plant systems. There was a massive dieback event of mangroves in the Gulf of Carpentaria through this time. And potentially, because this is in spring, the length of the fire season. Warmer temperatures don't necessarily equate to enhanced fire weather, but it is a big component of it. If we look at the deciles, in the deep orange there, it's the highest on record across a huge region of the country in maximum temperatures. We can look at the internal variability. Soils were dry, so the preceding months were dry. El Nino was strong, and the Indian Ocean dipole was in a mode that would have brought dry conditions to Australia. So using our system, this graph has quite a lot of information in it. If we have a look over on the far right-hand side of the graph, we've got 2015 at the end here. And in the lines is the median forecast of October 2015 in current conditions in the red and a low CO2 environment in the blue. The range around that is our ensemble spread. We perturb the initial conditions very slightly to capture the range of where reality might go, I guess, where the forecast might go, a little bit like the butterfly effect. And that range is shown here in these graphs. And you can see the model didn't forecast the record heat, but it was a record against its own climatology. So although it started to go a little bit cool by the end of the forecast, it really was capturing a lot of heat relative to how it normally behaves. And we can see over on the far right, outside of the graph, the mean of the climatology in the bars across, the faint lines. In the red is the mean of the current climatology, so from 2000 to 2014, and in the blue, the climatology of the low CO2 climate. And they're about a degree apart, which is the trend pretty much, which is really nice. Not the trend over this period, but the trend since around 1960. And if we have a look at the forecasts, in the blue dot, it shows you the 2015 forecast, and in the red dot, it shows you the current climate forecast. And those are about 1 degree warmer than the climatology. So in a low CO2 environment, it would have been a record heat compared to that climatology. It would have been really warm. For the current climate, it was not only really warm due to all those internal drivers, but it was another degree warmer again. And so really the increase in carbon dioxide since 1960 has meant another degree of warmth on that particular forecast. And it was 15 times more likely to break the previous record in the current climate than in a low CO2 climate. So these are really, I guess they make sense because they're obviously on the background trend. Now, if we start to get a bit more tricky, we can start to look at wet extremes. So this is one we tried for the wettest September on record in the Murray-Darling Basin, Southeast Australia. Another very impressive time series here. You can see the anomaly is well outside anything we've seen before, but it isn't on a background trend. If you look at that time series, you wouldn't really put any trend through that particular. So, internal variability. The negative Indian Ocean dipole was very strong during this time in September 2016. Although, to be fair, some of Chai's work also under our project in NESP 2.2, these sorts of intense negative Indian Ocean dipoles might be becoming more common. So, this might also be influenced by climate change. If we decompose or deconstruct the contributors to rainfall, for heavy rainfall you need a few components. You need a lot of moisture in the air. In this case, we've classified it with precipitable water. The blue means there's a lot, and you can see right across Australia there was a lot of water available. You also need instability in the air. You need that uplift to bring the moisture up into rain clouds and cause rain. And in this case, blue means strong uplift, and it was incredibly strong right across Australia. So we had all the components to make rain. So that was good. Our model was doing things well. This is the forecast. If we have a look, so again, that precipitable water is still in the top panel there. And if we have a look at how the carbon dioxide has changed things in September 2016 in the middle panel, you can see things are more blue than they would otherwise be in the current climate compared to a low CO2 climate. And this makes sense. We hear that we're going to have more moisture in the atmosphere, and that's true. In this for this event right across the tropics. And in the climatology below, you can see that is also echoed. Interestingly though, for subtropical Australia, in fact for most of Australia, that's not the case. Higher levels of CO2 are not driving increased precipitable water across the country, which I think is a really interesting outcome. Another component is that buoyancy. So you see in the blue, we had hugely enhanced buoyancy in September 2016, but if you have a look at the influence of carbon dioxide in the climatology, so now in the bottom plot here, actually it's enhancing a more stable climate. So the climate now compared to back in a low CO2 climate is more stable. It's just harder to rain. And so in 2016, it wasn't as strongly reduced, but it was still reduced. So if anything, the effect of the increasing atmospheric CO2 on the extreme September 2016 rainfall across Southeast Australia was minimal. And this was supported or in line with a study by Andrew King, saying that the warmth in the Eastern Indian Ocean, really that Indian Ocean dipole, increased the likelihood of the wet July-September in Southeast Australia by at least a factor of 2. I would suggest though that there is more to study when it comes to extreme precipitation. When we looked at the structure of the daily events, that had actually changed between a current climate and a low CO2 climate. So what was going on there? We know that extreme precipitation events, so those ones on the 1 hourly timescale, are expected to become more extreme. So really drilling down into finer timescales, I think, would make a really interesting follow-up study to this one. And further work can certainly be done. Another kind of event that we tried to use our attribution methods on was fire. Now this is fire weather. It's not anything to do with ignition or the state of how much vegetation there is, although this is February 2017, and so following on from the heavy rains through 2016, actually things had grown. So there was stuff to burn in this region. If we have a look at the deciles on the left-hand plot here, we're looking at the MacArthur Forest Fire Danger Index, which has issues of its own, but this is what we're going to use in this particular study. And we see that it was the highest on record through February 2017. And what about the background trend? Well, it's actually surprisingly patchy for this particular fortnight period that we looked at, February the 1st to the 14th, but through the region of the Sir Ivan fire, there was definitely an upward trend in the FFDI since 1960. If we have a look at the conditions leading into the fire, so this is a component of the Forest Fire Danger Index, which gives you some sort of indication of how dry the material might be. And temperatures were high, and that matches with the ongoing trend in January leading into February. And the trend in rainfall is not particularly strong, but generally downward in this region. And so we used a hybrid method. Our forecast was not great if we initialized it 20 days out to get an estimate of this particular component of the fire danger index, the drought factor. And so we actually got this from the observations, reducing temperatures by 1 degree. And we combined that with a forecast of the event. And so we forecast the temperatures, the relative humidity and the winds of the event. And we actually did okay. And you can see that the forecast reflects what the observed FFDI was. And if we have a look at the current climate versus a low CO2 climate, we can see that there were increased chance of FFDI, particularly in the north of the region. But this method could be improved. So Mitchell Black played a big role in this, and he's very experienced with these sorts of metrics, and there's actually a lot of work that could be done in this Another fun study we had was on frost, and this actually goes back to those changes in the circulation due to warming. So I showed you very briefly a change in the structure of the atmosphere due to increasing levels of greenhouse gases. And that changes the gradients of temperature from the tropics to the pole, and it can change where highs might be set up. Highs and lows might spend most of their time. And in this particular case, we found that there was a dynamic circulation pattern that was driving more cold air over the region in southwest WA in September 2016. In the models, though, perhaps their land surface schemes are not particularly advanced, and larger thermodynamic changes. So the actual column change in the greenhouse gas will lead to warming, and it still made these events less likely. But I was pretty excited because in this study, led by Michael Gross, he used our seasonal forecast system, but also the weather at home system, and results were very similar, which was really exciting to use a multi-method approach in one paper. So where to from here? Within the Bureau, we have a number of operational tools to identify extremes as they occur. Obviously, if someone's working on the bench, an extreme happens, they want to know how it sits in the climatology. And these sorts of tools are designed for people internal to the Bureau to be able to talk about this quickly. So one on the left is an aerial average for New South Wales. There was an anomaly of 2.58 and it flashes up red. It's the highest on the ranking, 105 of 105 years, and it gives you the other highs and lows previously so that they can be spoken about rapidly. This can also be done on a station-based approach. And for us, we have a long-term goal to build a framework from which to deconstruct the drivers of each event as it occurs. And so hopefully one day we might be able to do this quickly and add to these operational packages. So what do we want to do next? Well, absolutely. I think there's so much more science we can do around attribution of those more complex extremes like rainfall, wind, drought. And multi-method attribution is just really great. And so we can have the seasonal forecast-based method, but we can also use methods based on those climate models or weather at home or observation-based methods as well. At the moment, under the NEST program, we're actually trying to shift to the new Bureau of Meteorology seasonal forecast system, Access S2, which has a higher atmosphere and ocean resolution and better land physics and other physics as well compared to the old one, POAMA, which we were using in the previous studies. Of course, the development of these sorts of new products would mean we'd need some kind of interface for people to actually use these results. And we really would need to work with partners to do this best. Thank you.
Great, thanks Pandora for a really fantastic webinar. Just a reminder to everyone that if you do have questions, do quickly pop them in the chat box so we can address them. We do have a question from Will Howard, who was just asking for a bit more clarification around the 2018-19 summer heat. So that is the attribution saying it's impossible the heat could have occurred without anthropogenic warming, or that it's impossible for it to have been that hot? So David Crowley provided a bit of information on that, but did you want to just address that a bit more, Pandora?
Yeah, so I think, and I would probably defer to whatever David Crowley says. I think he's been in contact with Sophie directly. That is really around this extra amount of heat. So it's not whether a hot event could occur. Obviously they can, we still have variability, but it's the amount, this 1 degree over what we've seen before. Is that what David said?
Yes, pretty much. We also have another question from David, which is, which types of extreme events do we have the best prospects for attribution, and which ones are the hardest to link to climate change?
So as I was trying to get at in this presentation, really the ones that have a background trend in the same direction as the extreme are kind of easy to attribute because we understand what's driving the trend. We can spend our time doing an attribution study on that, and then when the extreme comes along, it's just a little bit more on top of that trend, and it seems to make sense that that attribution should be fairly straightforward. Those kinds of events that seem to buck the trend, that are well outside of the ordinary, they're record events, but they're really not in the direction of the trend, like that precipitation event in the Murray-Darling Basin. They're the ones that are a bit more tricky, and I think scientifically really exciting because we can really drill down into what's driving them. And again, those really complex events like fire weather or drought are also they need to be framed really clearly as to what exactly it is that you're attributing, whether it's a component of that. The drought study in Tasmania was really around the circulation changes there rather than the rainfall from them, simply because climate models can do that perhaps a bit more consistently or robustly in terms of a synoptic system of a 1,000-kilometre scale compared to a rainfall system of a very small scale over Tasmania. So, yeah, there's lots of exciting science to go forward with here, but some things are pretty hard.
Okay, our next question comes from Grant, who asked, what was the focus of the attribution study that looked at ecosystem function? Which ecosystem, and what was the event being investigated?
I'm assuming that was from that map of Australia, and I don't know which one it was, but perhaps it was coral and the coral bleaching event. And so it was the very warm ocean temperatures and their impact on the coral. I'm assuming that's the one that it was.
Okay. And one more question from David. What about the frost event that Michael Gross linked to climate change?
Yeah, so I'm always really interested in the processes behind these things. And so this was the, can you still see my slides? Yep. So this was the particular event, and it was throughout September 2016, the number of frost risk nights and the ranking of those relative to what we've seen before. And you can see in the deep purple on the right-hand slide, many of them were the most number of frost days on record since 1910. And what Michael Gross found was that it wasn't so much as the clear nights causing this frost, although there were clear nights. It was a very dry period in southwest WA. But it was this anomalous high pressure system off the southwest coast. And so with this, you get these anomalous winds up from the south advecting cool air over the region. So you've got anomalously cool air coming through in September that allowed those clear nights to work together with these cooler air sitting there, probably very stable conditions producing frost. And the really exciting thing for me is that in the Weather at Home system, it really captured this anomaly very well. And in the Poema forecast, it was a little bit shifted to the west, but still had the same sort of idea. And I thought that was pretty neat. Yep.
Okay. I just have a quick question as well. Like in the past, we've heard a lot of people through the media and whatnot say that you can't attribute or you can't link climate change to a specific event. So now all the methods that you've just been describing, it seems to me that it's quite clear that you now can do that. Would you agree with that way of thinking?
Yeah, so yes, absolutely. So I think, I mean, obviously the thing we really need to be careful with these model-based methods is, can the model capture this particular event? Is it fit for the task? And so that's why in that Lewis and Caroli study, that's what they did first. They compared with the observations. Could it capture the structure of the temperature anomalies as they are in the observations. And they did. And so, you know, that model's fit for that task, and it can go ahead. The same with the seasonal forecast method. We have to make sure that the event is forecast well in the first place before we can do anything. And that's the very first step we do with any attribution study, is testing our model, making sure it's fit for purpose, and then we can make statements about what's going on.
Fabulous, thanks. All right, we have another question. So which says, there was a lot of interest in the monsoonal event in northern Queensland earlier this year and the extreme rainfall associated with that setup. We were not aware of any attribution studies done for this event, but there was a lot of interest about whether this was a result of warming climate. Are there plans to look at this, or was this a result of the synoptic setup rather than a changing climate?
If my office mate was here over my shoulder, I'd be able to answer that question. He's doing a study right now on that event, really digging down into what drove it, so we'll be able to answer that very soon. As I said, because of the physics of a warmer atmosphere holding more moisture, we should see more extremes in these very short duration, high intensity events. At the moment, we're seeing that on the 1 hourly timescale, and we're starting to see it on the daily timescale in the north. There's a nice paper by, I can't remember the name. Anyway, it's just come out recently, and it's really showing up in many stations across the north of the country that we're seeing this evidence that there will be heavier precipitation for the same kind of synoptic event. So it's quite possible that there was a contribution from global warming, but we haven't done that attribution study.
Okay, and the person who asked that question also asks, who is the person, your colleague, that's working on that? Because they also work in the Bureau and would like to contact them.
Oh, Tim Cohen.
Tim Cohen, okay, lovely. All right, we do have one more question actually. Keep them coming in, we have a little bit more time. So Marion asks, there was a substantial time lag in between the events and being able to attribute them to climate change rather than natural variability. How long do these studies tend to take?
So one really nice thing is that compared to any other scientific paper going through review and being published, the Bulletin of American Met Society has kindly set about having some really, really keen and busy editors, and so you can submit studies about events from the previous year to them and should come out by the end of the year. So about 1 year. There are groups who are trying to do this much more quickly, and they tend to then come out not in the peer-reviewed literature, but they might use peer-reviewed methods. And so they might apply their peer-reviewed method to a recent event and publish it somewhere like The Conversation or in a newsletter. And that sort of thing has been happening more and more from groups. There's a group in the UK that's been doing that, and certainly some of our university colleagues here in Australia have been doing that too.
And Pandora, do they then go on to publish a peer review paper after they've done that, or? Sometimes.
Everyone's kind of busy. Yeah, so I'm thinking of the South African drought, and there was a very rapid attribution study on that, and I'm pretty sure that the peer-reviewed study is now coming following that. But that peer review process takes a really long time, and for the most part they find that because it's a method that has been used before, the framing is good, the model is good for this kind of variable, they should pass review quite easily. It just takes time.
Yeah. So David comments that you've already reported attribution results from the 18-19 summer heat. So that obviously didn't take a year. Were you using the other method you described?
Yeah, so that was from Sophie Lewis, and using methods that she used in earlier papers. And it's not published as far as I know.
All right, well, we don't have any other questions, so we might wrap it up there. Thank you again, Pandora, wonderful presentation, and thank you everyone for your time. Just a little plug for next month's webinar. So the Earth Systems and Climate Change Science webinar for next month in May the 21st will be provided by Professor Neil Holcomb from the University of Tasmania. And he'll be talking about heat waves, including their impacts, causes, and their predictability as well. So we'll get in contact with you with more details around that, including registration in the following weeks. And also, finally, just a very quick reminder that we do record these webinars and we put them on our website by the end of the week. So if you want to watch it again, or you've missed it, or you know someone who's missed it, please do head to the Earth Systems and Climate Change website, which is up on the screen now. And also, if you have any more questions for Pandora or anyone in the Hub, do feel free to contact us at that info@nestclimate.com.au, and we'll pass on your questions to Pandora or to anyone else. So thank you very much again for attending our webinar, and we hope to see you at the next one. Thank you.